Hi everyone. In this section we'll look at diffraction gratings. A diffraction grating is a number of equally spaced parallel slits, and it can also be called an interference grating. The number of slits in the diffraction grating is capital N, and they're separated by distance d. The analysis is very similar to what we did for Young's double slit experiment. So if we imagine parallel rays incident on a diffraction grating, the distance that one ray travels further than another will be equal to the path difference delta r, which equals d sine theta. So we end up with the same formulas as we had for constructive interference and destructive interference. A difference with a diffraction grating opposed to a double slit experiment is that now there are many more wave sources. So this will result in more complete constructive and destructive interference, leading to sharper, more well-defined fringes. Another difference is that generally for a diffraction grating, since we'll have many slits in a small space, d is very, very small, which means that theta is actually large. So we don't want to use the small angle approximation here for a diffraction grating. Diffraction gratings are often used to separate colors of white light. So before we were looking at monochromatic light, which was light of a single frequency or color. Now often we'll look at white light incident on a diffraction grating or multiple wavelengths of light. We can see that the angles of the fringes depend on lambda, so this means that there'll be different colors of light producing different constructive interference fringes at different angular positions. So if we had white light incident on a diffraction grating, there would be a large white central maximum, or a bright white central maximum, and then we would have colored fringes at different angles. Sometimes for a diffraction grating, we'll be given the number of slits per unit length, for example, the number of slits per millimeter, and then we can divide in order to find the slit separation. A diffraction grating that's used for visible light would generally have about 1,000 slits per millimeter. And as the number of slits per unit length is increased, this leads to sharper and clearer interference fringes. Example 5, the wavelengths of the visible spectrum extend from approximately 380 nanometers, violet, to 750 nanometers, which is red. Find the angular limits of the first order visible spectrum produced by a plane grating with 600 slits per millimeter for each wavelength. B, do the first order and second order spectra overlap, and does this depend on the grating spacing? Okay, so I have the two wavelengths, and then I have the equation we want is sine theta equals m lambda over d, and we can find the slit spacing here by taking, since we have 600 slits per millimeter, if we invert that, we get the millimeters per slit, which is 0.00167. So finding m equals 1, the first order angle for each color, we have red will be sine inverse lambda over d, so sine inverse 750 times 10 to the negative 9 meters over 0.00167 times 10 to the negative 3, which gives 26.7 degrees. Then we have theta violet, which is sine inverse 380 nanometers over 0.00167 millimeters, and it's 13.2 is the angle for violet. Okay, so part B asks if the first and the second order spectra with these two wavelengths will overlap. So I basically just repeated this calculation for the second order. So now plugging in m equals 2, m equals 1, I was just rewriting that, but here this is m equals 2. So for 380 nanometers, which is violet, we get 27.1 degrees. And then for red, we have 63.9 degrees. So we have our first order, m equals 1, ranges from 13.2 degrees to 26.7. And then for m equals 2, this ranges from 27.1 to 63.9. So no, these don't overlap. It's close, but they don't overlap. And the question was, does this depend on D, the slit spacing? So yes, these angles depend on D. And so does whether or not they overlap. If we check the second and third, we might have another answer there. But in general, for the first order, if we have 2 lambda 1, so twice the smaller angle greater, twice of the smaller wavelength greater than the larger wavelength, then these 2 orders won't overlap. We've been talking about a type of diffraction grating called a transmission grating, where light passes through these narrow slits and then interferes. Another type of diffraction grating is called a reflection grating, where fine lines are etched onto a metal or a glass surface, and then when light is incident on this surface, the grooves will separate the light, and depending on the angle at which the light hits this surface, it will travel a different distance, leading to a path difference and then again interference. So some real life examples of this are a CD. Well, a CD has many narrow grooves. It's used to encode information, but if you shine a laser onto that CD, you can actually reflect a diffraction pattern because of those grooves. It's a reflection grating. An example of a transmission grating is peacock feathers. They're made of very fine lines of melanin, and we see all of these colors in the peacock feathers because of the light passing through those narrow lines and then interfering and separating as the interference fringes depend on the wavelength. And we'll use a diffraction grating, or I guess we'll watch a video of it being used in this case for a spectrometer. So diffraction gratings are also used in spectrographs, which are used to measure properties of light based on the interference fringes. And we'll use that in the Balmer series.